Hello everyone, my name is Vidushi Dadu. I am a 4th year PhD student at UCLA. In this talk, I will present our work on PolyGraph, exposing the value of flexibility for graph processing accelerators. This work is done in the PolyArc lab at UCLA. Graphs are fundamental data structures in many critical applications like Google Maps, recommendation systems, and many more. Motivated by this, there have been significant efforts in designing hardware accelerators for graph processing. However, it is very surprising that even though these accelerators are designed for the same set of input workloads, their microarchitecture design is vastly different. This difference raises a question of which of these accelerators is the best choice, or is even one of them always a better choice for all inputs? To answer this question, we evaluated 4 prior accelerators on a broad set of input workloads and graph types. In this graph, the y-axis represents the speedup of per case best over per case worst accelerator. We find that there can be an orders of magnitude performance differences even among the application-specific architectures. More interestingly, all of these prior accelerators perform best on at least one of the scenarios. Therefore, we can neither rule out one of these accelerators nor choose the optimal one. Such confusion in the relationship between the accelerator design and performance calls for a systematic analysis. For this analysis, we define performance as the multiplication of memory efficiency and work efficiency. Here, memory efficiency is defined as the number of contiguous DRAM accesses required during program execution, and work efficiency is defined as the number of updates required for algorithm convergence. Both of these factors are heavily influenced by the factors on the left, out of which 2 are the input, graph, and workload types, and the third one is graph algorithm variance. This dimension represents accelerator characteristics and is the key focus of this paper. So, as we cannot change the above 2 factors, in this work we will study graph algorithm variance and try to answer whether is it worth it to support flexibility across algorithm variance, and if so, how would that architecture look like? In this talk, I will first discuss the design space of algorithm variance and how they create trade-offs for memory and work efficiency. Then I will discuss our proposal for PolyGraph, where we support flexibility across these variants. I will then discuss our evaluation results and then conclude. Let's start with the design space for graph algorithm variance. Our graph algorithm variant taxonomy is based on the vertex-centric execution model. Therefore, I will first give background on vertex-centric model and then describe the options it provides us. Let's consider this input graph, which we might split into multiple temporal slices such that each slice fits into on-chip memory. These slices are then executed over time. As the slice fits into on-chip memory, the working set is controlled here. Within a slice, the execution is performed at a vertex granularity. Here we are showing only a subset of a temporal slice 1 for brevity. The first step is to access the outgoing edges. In the second step, the destination vertices are updated using some user-defined functions that depend on the graph workload we are implementing it for. And then finally, in the third step, based on some condition, these destination vertices may be iteratively activated. The algorithm converges when there are no more active vertices. Now this provides 4 important options. First option is the order in which we would schedule these slices. The second option is whether we will send the messages to the outgoing edges or we will receive the messages from incoming edges. The third option is whether we will make these updates visible to the other vertices immediately or after a synchronization phase. And then finally, the order in which we execute these concurrently active vertices will significantly impact performance. In the next few slides, I will formally define each of these dimensions and then discuss the insights for its impact on memory and work efficiency. Update visibility defines the granularity at which updates are made visible to the subsequent vertices. For graph synchronous, this granularity is all slices of the graph, and therefore we have the synchronization phase after all slices of a graph are done. In slice synchronous, this synchronization phase is after every slice. And finally, in asynchronous, these updates are made visible immediately and no synchronization phase is required. As the delay distance is minimum in asynchronous execution. It is best for work efficiency, while graph synchronous is usually better for memory efficiency because it can implement many memory efficient optimizations. For the asynchronous execution, where updates are made visible immediately, the vertices could also be dynamically activated and executed. This opens up opportunities for scheduling these dynamically activated vertices in different orders. For insight, consider a shortest path algorithm. Here, if we prioritize a nearer node first, we could converge the algorithm with much lesser work as compared to, let's say, a memory efficient order. We call this special data dependent ordering as work efficient order. There can be other orders like creation order and locality order. However, in our experiments, we find that these orderings have less impact on overall performance as compared to work efficiency order. For the slice scheduling dimension, there can be two options. The first is non-sliced, where the execution is performed on the whole graph, while for the sliced variant, the execution is performed slice by slice. Here, the graph is split into multiple slices such that working set fits into on-chip memory. This leads to higher memory efficiency. However, there are two overheads with the sliced variant. The first one is the barrier which is required between every slice in order to switch these slices from the scratchpad memory. This could be a higher overhead when the work during slices is less. And another benefit of non-sliced could be a better work efficiency. The reason is because in non-sliced, the cross-slice updates are not delayed, leading to higher work efficiency. There can be different scheduling variants of the sliced variant, and that trades off memory and work efficiency. In our evaluation, we find that for PolyGraph, these do not show much difference in performance because PolyGraph uses large EDRAM memory, leading to coarse-grained slices. Now that we have developed an understanding of how the graph algorithm variance trades off memory and work efficiency, the final decision of optimal algorithm variant depends on how sensitive the input graphs and workload types to memory and work efficiency. For example, there can be low diameter graphs or high diameter graphs. For low diameter graphs, the vertices are highly connected, making them very hard to partition. Because of this, it is hard to exploit the hit rate in them, and therefore memory efficiency is extremely critical. For high diameter graphs, in contrast, work efficiency is more critical. This is because any wrong updates may travel deep into the graph without being blocked by high degree nodes as would be in a low diameter graph. For workload types, let's consider order sensitive shortest path algorithm. Here, the path that you prioritize will determine how fast the algorithm will converge. However, for non-order sensitive workloads like GC and inference, the required work is always same and the memory efficiency is the bottleneck. Overall, in this section we learned that inputs may be sensitive to either memory or work efficiency, and in order to support different kinds of input graphs and workload types, we need to allow flexibility across algorithm variants. Now let's move to how do we support this flexibility in our PolyGraph. For supporting flexibility in the update visibility and vertex scheduling dimension, we need to be able to reorder the vertices using a data-dependent priority order, and since this has to be done dynamically, we need to ensure that these are done at a high throughput to match with the throughput of vertex computation. SIMD execution models are insufficient for this scenario because in vertex-centric models, the vertices require varying amount of work proportional to their degree, and this work may often be too small to utilize all SIMD vector lengths. Therefore, we propose to use a data flow execution model that at least solves the utilization problem as different lanes are independent and is also performant. In a data flow model, the computation is expressed using memory and compute nodes, and the edges between them represents the explicit dependencies. I will first explain how the data flow model works for a shortest path algorithm written in a vertex-centric model, and then explain how do we overcome its fundamental limitations for supporting our algorithm variants. For the shortest path algorithm, here we have two memory nodes to load the active vertices and their current distances. Then we will perform the first step to access its outgoing edges. Then the destination vertices are atomically updated. Finally, based on a condition, these destination vertices may be activated, that is stored in some memory location for active vertices. Now, there are two main limitations of the traditional data flow model. First, it does not have any native support for data-dependent ordering, and relying on a software-based priority queue would dominate the execution time. And second problem is, some tasks like atomic update would best work when executed near data. The reason is that these involve long latency remote reads and writes, and executing near data would save a lot of network traffic. Therefore, what we really need is to extend the data flow model with tasks and have a way to express when and where would this task be best executed. Here we propose our task flow execution model, where the tasks are a group of data flow nodes that are scheduled together in time and space. As shown in yellow color, these tasks represent explicit dependencies among tasks and are triggered when all operands of a task are available. These operands are basically the incoming edges for the task nodes. When a task node is annotated with priority, that determines the scheduling order, and when a task node is annotated with an ID, that determines the core where the task should be executed. This unified representation opens up the door for efficient data flow processing with dynamic task parallelism. For the hardware, we start with a hardware known to work well for the traditional data flow execution. It has a CGRA computation substrate for compute nodes and an address generation module for memory nodes. The control core is responsible for scheduling these nodes onto their corresponding hardware. The control core also schedules the connections across them. For implementing task flow, control core will be insufficient as it cannot do data-dependent ordering at a high throughput. Therefore, we introduce a task management unit in the data path. This task management unit has a hardware-based priority heap, which can provide a high throughput of one task NQ and DQ per cycle, and it can reorder the tasks based on a user-defined priority. We also have a task queue overflow module that checks whether there is a space in this task scheduler or not. If there is no space, it will check whether the current task is a very high priority task. If so, it could be stored in some reserved entries, otherwise it will be sent to memory. We also have a special module called Task Scheduler. This is specialized for graph processing, and it checks whether there exists a task with the same vertex ID or not. If so, that task will be coalesced to reduce the redundant tasks during execution. Now, in order to show how we support spatial scheduling, we need to consider when we tile this a single PG core. The new hardware additions will be a router and a unit for checking which tile this current task belongs to. If the current task should be scheduled at a remote core, it will be sent via router. Otherwise, it will be pushed to the local task scheduler. On the overall flow, the control core will now be responsible for pushing only the initial tasks, and the task scheduler will now be responsible for really scheduling the work on the memory hardware units. As we saw that because of the high throughput of task scheduler, there can be many prefetch requests pending at a time, which will lead to a deep prefetch pipeline. This is crucial for graph processing, where memory level parallelism is usually the bottleneck. Thanks to the deep prefetch pipeline, we can get a high throughput computation and also a new task NQ, which will pass through this highly pipelined task management unit. To connect the pieces, the final PolyGraph core has few other components. First component is a shared memory location in on-chip EDRAM. This location maintains metadata to hint the hardware when it should switch slices when executing with the task flow execution model. This is interesting because it trades off for the reuse when iterating over a single slice and work efficiency when switching to the next slice to reduce the cross-slice delay distance. In order to support both sliced and non-sliced variants, we add a region translation unit in the address generator. This unit maintains the address ranges of the pinned regions and can enable the on-chip EDRAM to both behave as a cache or a scratchpad when needed. Finally, we identify that there is a benefit in dynamically switching variants, even during the execution of a single algorithm. This is done at a very coarse grain and hence can be supported at the control core itself. Finally, in order to scale this single polygraph design, we connect it with a very efficient mesh network. This network includes a high bandwidth 32-byte network for the accessing edge data and 3 scalar networks for the task data. We use these 8-byte networks for the task data because tasks are very fine-grained, and in order to achieve high throughput, we need multiple networks. We also propose a novel multi-level spatial partitioning policy to balance locality and load. Let's move to the evaluation. We implemented PolyGraph using a custom simulator where different pipeline stages represents the different steps in the vertex-centric execution, and each of these could be configured according to the algorithm variant that PolyGraph is currently implementing. We evaluated against 4 prior accelerators according to the graph algorithm variant that they specialize for. We tried our best to be true to the original proposals versus keeping a fair field for all of them. We also evaluated a version of PG single algorithm that implements the best algorithm variant that we found out after doing a design space exploration across all dimensions. We kept similar architectural characteristics for all baseline accelerators. We used practical graphs for evaluation, with many of them requiring more than 2 or 4 slices. In the first graph, here we show the memory versus work efficiency trade-offs of different algorithm variants on PolyGraph. The y-axis shows the throughput in terms of the giga traversed edges per second, and the x-axis is the work efficiency. The first column shows the ordered workloads, while the second column is for unordered workloads. For low diameter graphs, we find that asynchronous slice variant performs the best as it is more close to the ideal performance. The reason is because the slice variant optimizes for work efficiency that is critical for low diameter graphs. For high diameter graphs, non-sliced variant is better because this variant idealizes work efficiency. For the dense frontier workloads, for these workloads, the active vertices are generally high during execution, and because of this, memory efficiency also becomes a critical factor, and we find that slice synchronous performs the best because it balances the memory and work efficiency better. Overall, we propose a simple heuristic tree-based approach that can accurately predict the better algorithm variant for the given inputs. For the overall comparison, we normalize the performance to a 24-core SKL CPU, and we split the performance comparisons among different graph and workload types. For high diameter graphs, GPUs gives performance speedups because of the high density of computation units over CPUs. We evaluated against only one accelerator here, which is the best performing geomean accelerator. The GraphPulse implements a variant of asynchronous with locality vertex scheduling and sliced round robin scheduling. It performs better over GPUs because of its efficient crossbar network and also because of its asynchronous execution. PG single algorithm improves performance due to its work efficiency ordering. However, as we can see that it is not always optimal because of the inefficient sliced variant. PG multi-algorithm can identify that high diameter graphs prefer to use non-sliced variant and can see an exponential performance gain due to this choice. For low diameter graphs, GraphPulse see a significant performance gains over GPUs because the sliced variant improves memory efficiency significantly. PolyGraph single algorithm improves due to work efficiency benefits. And then finally, PolyGraph multi-algorithm shows some benefits due to dynamically switching to the optimal variant at different iterations of the algorithm. For vector workloads, slicing is not that critical because of their streaming memory access is highly efficient. PolyGraph gives speedup for these vector workloads because of its asynchronous execution. Multi-algorithm variant gives speedup because of dynamic flexibility in collaborative filtering. Overall, we achieve 1.93x speedup over the best geomean accelerator GraphPulse, and with flexibility, we can achieve 2.7x more speedup. In conclusion, we proposed a task flow execution model that can handle a challenging form of parallelism with accelerator-like efficiency. We also observed that algorithm variants can fundamentally impact performance, and it is the sensitivity of inputs to this impact which is creating the need for flexibility. In broader terms, for accelerators, it is often seen that more flexibility leads to more efficiency and not less according to the common intuition. Here are a few examples, and our work just puts more emphasis on this observation. Thank you.